Let's see. 2.2.1, the IUPAC name of compound E. Okay. So let's go ahead and take a look at compound E. We have a carbon with a double bond. So that is a characteristic of an alkene. Okay. How many carbons do we have in our longest chain? Let's see. If we start numbering from this carbon, we're going to have 1, 2, 3, 4. Even if we go down, we still have 4 carbons on our longest chain. So that seems like we have 4 carbons on our longest chain. So for 2.2.1, we know that we have but. Let's go ahead and figure out everything else. We have to start numbering from the side closest to the double bond. Okay? If we are saying that we have 1, 2, 3, 4 carbons, then if we start numbering from this side, then we will get to the double bond first, okay? Because if we start numbering from this side, then the double bond will be on the third carbon, and that's not what we want. We want the side closest to the double bond, which will be this side. So this is our longest carbon chain, okay, which is but. So we've built one in one because our functional group is on the first carbon, okay? And as you can see, we have methyl and methyl. One methyl is on, so we have 2 point, so this is the second carbon and this is the third. 2.3 dash dimethyl but one in, okay? Right, so that is our IUPAC name of compound E. 2.2.2, we are looking for the IUPAC name of H. So let's go ahead and take a look at H. Okay, on H, carbon double bonded to oxygen. And this carbon is sandwiched by 2 other carbons. That is a ketone. So I'm going to have butane 2 on, okay? I think even if you don't include this 2, it would still be correct. Because if you have 4 carbons and on a straight chain, right? And it is a ketone, then the oxygen bonded to the carbon should be on the second carbon. If that is not the case, then it becomes an aldehyde. So butane 2 on. But I also think that if you don't put these 2, you would still be correct. That is 2.2.2. Okay, let's move to the question that follows. We have butane 2 on. Okay, right. 2.3. 2.3, we are looking for the structural formula of compound B. So let's go ahead and take a look at compound B. That is 2.3.1. So compound B, a carbon with 3 hydrogen, followed by 3 carbons with 2 hydrogen each. So 1, 2, 3 with 2 hydrogens each. Okay, and then after that we have another carbon which is double bonded to an oxygen, one other oxygen which is bonded to its carbon. Okay, so this is the structure you're supposed to have for compound B. Obviously, we need to fill out our hydrogens. Okay, you cannot leave it like this. Only I can do that and not you. So this is the structural formula of compound B. Let's see if we have the correct number of carbons. So we have 1, 2, 3, 4, 5, 6. This is 1, 3 makes it 4, 5, 6. I think we are good to go. Okay. Structural formula of compound C, 2.3.2. Let's go ahead and take a look at that. 2.3.2, structural formula of compound C. We have 4-ethyl-3.3 difluorohexane. So I'm going to start by taking care of hexane. I need 6 carbons. So 1, 2, 3, 4, 5, 6. On the third carbon, I have difluoro. There we go. And on the fourth carbon, I have ethyl. Ethyl will look something like this, okay? I have a branch with 2 carbons, right? So now I just need to fill out my hydrogens and I am done, okay? So let me leave that for you. Go ahead and fill out all the hydrogens that are required. Okay, right. So this is the structural formula of compound C 2.3.2. 2.3.3 general formula of the homologous series to which compound E belongs. Compound E is an alkene, so the general formula should be CnH2n. Yes, not plus 2, not minus 2, just CnH2n. 2.3.4 structural formula of functional group of compound F. Compound F, carbon double bonded to an oxygen sandwiched by 2 other carbons. That is a ketone. The structure of the functional group should look like this. Okay, we should not have carbons on these. We should not have hydrogens on these 2 carbons. So if you put hydrogens on those carbons, then it is then not correct. Okay, you are now drawing the structure of propanol, right? And no longer the functional group of ketones. That is 2.3.4. 2.3.5, IUPAC name of the alcohol needed to produce compound B. So for compound B, we have the structure. Let's use the structure instead. Okay, if you come here and put a line, the carbon that is bonded, or the part of the structure that is bonded to 1 oxygen is from the alcohol. Which alcohol has 1 oxygen? Not 1 oxygen, but 1 carbon, okay? That is methanol, right? Yeah, the alcohol with 1 carbon is methanol. 2.4.1, 2.4.1, we're looking for letters of a compound that is the letter of a compound that is a functional isomer of compound G. So if you take a look at compound G, we have an acid because of the functional group, which we can identify right there. And that acid has 1, 2, 3, 4, 5, 6 carbons. So we are looking for an ester with 6 carbons. It will be a functional isomer of compound G. If you look at B, in B we have 6 carbons. So the answer to 2.4.1 is B. That ester right there with 6 carbons will be a functional isomer of G. And then 2 compounds that are chain isomers of each other. Okay, G and D. D is hexanoic acid. It is a straight line hexanoic acid. Okay, and compound G, it is an acid with 6 carbons, so they should be chain isomers of each other. Same molecular formula, just different chains.
Is this organic compound a primary, secondary, or tertiary alcohol? We're supposed to give a reason for the answer. So let's go ahead and take a look. Right, so in compound A, let's just zoom in on compound A. We have 1, 2, 3, 4 carbons. So that should be butanol, right? We do have a branch here that I'm not accounting for, but we're going to take care of that. So let's take a look. Let me just circle that. This is our longest chain. We can take this as our longest chain. Even though if we go up, we would still get the longest chain of 4 carbons. Let's just take that as our longest chain. And then we have a branch on the second carbon and the functional group. Right, that is what we are dealing with. Let's go back to the question. Is it a primary, secondary, or tertiary alcohol? Well, this is a tertiary alcohol. So let me just write that down first and then explain to you why I'm saying so. This is a tertiary alcohol, right? Why do we say that it is a tertiary alcohol? It is because, take a look at these. This carbon that is bonded to OH. The carbon that is bonded to OH is bonded to 1, 2, 3 carbons, right? So if the carbon that is bonded to OH is bonded to 3 carbons, it makes it a tertiary alcohol. If it was bonded to 2 carbons, it would make it a secondary alcohol. And then if it is only bonded to 1 carbon, it would make it a primary alcohol. So right, it is a tertiary alcohol because the carbon bonded to OH is bonded to 3 other carbons. There we go. So that is 2.1.1. Let's take a look at 2.1.2. Write down the IUPAC name for the above mentioned compound. Okay, so like we have figured out, we have 4 carbons on our longest chain. So that is butane. And then which carbon is our functional group found? Well, if we start counting from the left, we have 1, 2, 3. But if we start counting from the right, we have 1, 2. So clearly we have to start numbering our carbons from the right. So we're going to have butane, 2, all. But we need to account for that branch there. We need to account for that branch. So on the second carbon, we have 2-methyl. So there we go. 2-methyl butane 2-ol. That is the IUPAC name of our compound A. 2.1.3. 2.1.3. The above mentioned compound undergoes an elimination reaction. Write down the structural formula of the product that is formed. Elimination reaction. So let me just write that structural formula without condensing it. So this is OH, and then hydrogen. We need another. Okay, here we have a branch, so let's put that there. And then elsewhere we have hydrogens. Okay, so which elimination reaction can an alcohol go through? Because this is an alcohol that you're dealing with, right? So the elimination that an alcohol can go through is dehydration. It is dehydration. The alcohol loses 1 hydrogen and an OH, right, making it H2O, hence dehydration. That is the only elimination reaction alcohols can undergo through, right? So it means that the structural formula of the major product formed should be an alkene, right? This question is very specific. Major product, right? We have a major product and a minor product for these reaction. We have a major, well, for the product of an elimination reaction of alcohol, right? Dehydration. We have a major product and a minor product. So this is just the alcohol. This is not the answer. This is not the answer. This is just the alcohol. We just draw in the structure of the alcohol so that we can better make sense of it. So the major product of dehydration that compound A will undergo will look like the following. So we have 1, 2, double bond, carbon, carbon. So there we go. And then hydrogen everywhere else. Hydrogen everywhere else. So 4 bonds on that carbon. It is satisfied, and let's just fill out hydrogens everywhere. So let's check the number of bonds. This 1, 2, 3, 4. So everything is fine. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Right. You have to calculate the number of bonds to avoid making any mistake. We also need our branch. I'm forgetting to put the branch here. Because we have a branch here on the second carbon. So we don't have a hydrogen here, but rather we have a branch. So that is what we have. That is what we are dealing with. Let's check if the number of carbons is still intact. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I'm happy with that. All right, let's move to the question that follows. 2.2, 2.2.1. Consider the organic compound B. 2.2.1. Define the term functional isomer. Okay, so compound B is pentane 3-on, so that is a ketone. But well, the question wants us to define the term functional isomer, so let's go ahead and do that. Functional isomer, organic compounds with the same molecular formula but different functional groups. Same molecular formula but different functional group. That is a functional isomer. And then 2.2.2, I'm expecting that the question is gonna have something to do with isomers. Write down the homologous series to which the above mentioned compound belongs. Okay, compound B. This is 2.2, and 2.2.2 is a sub-question of 2.2.2. Okay, I was starting to ask myself which above mentioned compound, because I was thinking 2.2.1, but it is compound B that we are referring to. So compound B is a ketone, but the name of the homologous series is actually not ketone. It is ketones. It is in plural, by the way. Yeah, it's one of those things that we usually overlook. But the name of the homologous series is not ketone. It is ketones. Yeah, if you go to your exam guidelines, that is exactly what you're going to find. You're not going to find the homologous series ketone. No, the homologous series is ketones, right? We're just being, more precise. We live in no stone unturned. Okay, that is 2.2.2. Let's do 2.2.3. IUPAC name of its functional isomer. So the functional isomer of ketones is aldehydes, right? The functional isomer of ketone is aldehydes, right? They have the same, a aldehyde looks very similar to a ketone, but the only difference is that the double bond oxygen is at the end. So here we have pentane 3-on. So the ketone that you're looking for is pentanol. That is, the aldehyde, not the ketone, I meant. The aldehyde that we're looking for is pentanol. Pentanol and pentane 3-on are functional isomers. So what are we looking for? IUPAC name of its functional isomer. Oh, okay, we're done then. We're looking for the IUPAC name. I thought we were looking for the structure, right? But we're just looking for the IUPAC name. The IUPAC name is pentanol, right? 2.2.3. What about 2.2.4? Letter that represents its positional isomer. So we are dealing with pentane 3-on, right? So the positional isomer is pentane 2-on. It has only one positional isomer, right? Because we have 1, 2, 3, 4, 5 double bond oxygen, right? If you put this oxygen here, it is pentane 2-on. Same is true with when you put it here, you'll still have pentane 2-on, because we have to start numbering from the side closest to the functional group. So we're looking for pentane 2-on here on our table. Letter that represents its positional isomer. Okay, let's take a look. Pentane 2-on looks to be compound E. It looks to be compound E. Because take a look at compound E. We have 1, 2, 3, 4, 5. So that is where our pent is coming from. And then on the second carbon, double bond oxygen. So there we go, pentane 2-on. That is compound E. So the letter that represents its positional isomer, the answer is E there. The answer is E. It is compound E, pentane 2-on. Write down the balanced equation using molecular formula for the complete combustion of compound F. So let's take a look at compound F. Compound F is 1, 2, not 2 anymore, but actually 3, right? So we have 5 carbons in total. So that is C5. How many hydrogens do we have in total? We have these 3 here. We have these, which gives us 6, and we have 3. So that is 12, right? So H12. And then it is a combustion reaction. So it is excess oxygen to give us CO2 plus H2O. We just need to balance this equation. So C5, C1. What do? We put 5 and put in 5, the carbons are balanced. And then we move to the hydrogen. H12, H2. So we put 6 in attempt to balance the equation. And now take a look at this. We have O2 here, and here we have 5 multiplied by O2, which is 10, plus 6 multiplied by O2, which is 6. So this is 16. And then in order to get 16 on the left hand side, we must multiply with 8. So there we go. We have our balanced combustion reaction. Here we go.
Homologous series to which compound B belongs to. So let's go to our compound B and see what is happening. It will be easy to see that compound B is an ester because of this functional group that we have here. Compound B is an ester. So the answer to 2.1.1, that compound B is an ester. And then the second question, 2.1.2, we're looking for the IUPAC name of the same compound. So this is how you actually name an ester, ladies and gentlemen. You're going to come here to the structure and you're going to put a line that divides the oxygen with the double bond from the oxygen with the single bond. And then the part of the structure that has the oxygen with the single bond is coming from the alcohol. And the part of the structure that has the oxygen with a double bond is coming from the acid, because we know that in order to form an ester, you need an alcohol and an acid in the presence of H2SO4. So let's look at our alcohol. Our alcohol that was used in making this ester is methanol. Why are we saying it is methanol? Because of this single carbon right here. And the acid that was used to make this ester is propanoic acid. Why are we saying so? These 3 carbons that we have there. So when we name this ester, the name is going to be methyl propanoid. Methyl propanoid. Right. So this methyl here is coming from the fact that the alcohol that was used is methanol. If the alcohol that was used was butanol, then the name would start by saying butyl. And then the propanoid is coming from the acid that was used, propanoic acid. Let's move to the second question, 2.2 and 2.2.1. An alcohol and an acid are heated in the presence of concentrated sulfuric acid to form compound B. Write down the role of the concentrated sulfuric acid in this reaction. So sulfuric acid in an esterification acts as a catalyst. So the answer to 2.2.1 is catalyst. It acts as a catalyst. It speeds up the reaction. You can also say that. And then the answer to 2.2.2, names of the alcohol and the organic acid used to prepare compound B. So we have already deduced which alcohol was used and which acid was used when we were naming our compound B, right? So now we're just gonna say the alcohol that was used is methanol and the acid that was used is propanoic acid. The acid that was used is propanoic acid. 2.2.3, name of the type of reaction that is taking place. Obviously the name of the reaction that is taking place is esterification. And other books will say condensation, which is also correct. I see that option time after time in memos. That is 2.2. Let's move to 2.3. So in 2.3, from the table above, consider compound C. So let's go to compound C and see what I have. Compound C, we have an acid. This is the functional group of an acid. Ethanoic acid to be specific. Let's go to the questions. 2.3.1. So the first question, 2.3.1, write down the name of the functional group of compound C. So we've already deduced that compound C is an acid, right? The name of the functional group of acids is carboxyl. So we have carboxyl group. That is the name of the functional group. And then 2.3.2, to which homologous group does compound C belong to? It is the carboxylic acid. That's an easy question to answer. It is a carboxylic acid. 2.3.3, differentiate between the terms functional group and homologous series. This question is actually just asking you to define homologous series and functional group. So let me just remind you, homologous series is a series of organic compounds that can be described by the same general formula. A series of organic compounds that can be described by the same general formula. While functional group, on the other hand, is a bond or an atom or a group of atoms that determines the physical and chemical properties of a group of organic compounds. There we go. You just need to define functional group and homologous series for 2.3.3. 2.4 for the table above, from the table above, actually, consider compounds A, D, and F. And then the first question, write down the homologous series to which they belong to. So let's go to compound A. Compound A, we have an OH, which is the functional group of an alcohol. So we know that compound A is an alcohol. And then compound D, we also have another OH, so that is another alcohol. Let's look at compound F. It ends with ol, so we have another alcohol again. So A, D, and F are alcohols as far as the homologous series is concerned. So the answer to 2.4.1 will be alcohols, because A, D, and F are all alcohols. 2.4.2, compound A and D are isomers. As what type of isomer will they be classified? So let's go to A and D. A and D. So A, let me just write down A real quick for the sake of clarity. So for A, we have something like this. We have hydrogens everywhere else. And then let's look at D. So for D, we have condensed structural formula, which we're gonna write in full now. So we have a carbon with 3 hydrogens. We have the second carbon, and then on the second carbon we have 1 hydrogen and an OH, and then the third carbon with 3 hydrogens. So what type of isomers is compound A and D, not B? Excuse me, compound A and D. So compound A, the OH is on the first carbon, and then for compound D, the OH is on the second carbon. So they have the same molecular formula, but just different position of the functional group. So those are called positional isomers. So 2.4.2, the answer here is positional isomers. They will be known or referred to as positional isomers, compound A and D. The third question, 2.4.3, we asked to draw the structure of compound F. Let's go ahead and look at compound F. So for compound F, 2-methyl propane 2-ol. So let's start with the prop. So as soon as we see prop, we know that we need 3 carbons. So we have 1, 2, 3, and then 2-ol. This 2-ol tells us that the OH is on the second carbon. So let's have that OH right here. And then this 2-methyl, we have a branch on the second carbon. So we're gonna have 1 carbon there, and then now we just left out with the hydrogens, and we have the structural formula of compound F just like that. Let's go ahead and move to 2.5. So 2.5, we're interested in compound G and compound E. 2.5.1, we're supposed to name compound G. Let's go to compound G. So compound G, the first thing that we must look for is the longest carbon chain. It is easy to see that this will indeed be our longest carbon chain. Let's count that. 1, 2, 3, 4, 5, 6. That is hex. And then as soon as I see BR, I know that it is a haloalkane, right? So it will be hexane. It will be hexane. Now I'm just left with the branches. Where do I start numbering? If you start numbering from the left, on the second carbon, you have Br, you have bromo. And then if you start numbering from the right, on the second carbon, you have methyl, you have dimethyl, right? So the question now is, what takes preference between a branch and a halogen? Well, according to the exam guideline, nothing takes preference between the halogen and the branch. You just have to start numbering from the side that will lead to the smallest number. What do I mean by that? If we start numbering from the left, then we're going to have 2 for bromo, right? And then this is 2, 3, 4, 5. And then we're going to have 5,5 for that dimethyl. And then these numbers will give us 12. If we start numbering from the right, we're going to have 2.2 for the dimethyl, right? And then we're going to have 5 for the bromo. So this is 2 plus 5, which is equals to 9. If we start numbering from the right, we have the smallest number, and that's what we need to do. Nothing is going to take preference between the halogen and the branch. So we're going to have 5 bromo. We're going to have 5 bromo dash 2.2 dash dimethyl hexane. 2.2 dash dimethyl hexane. And that is the name of our compound G. The last question, structural formula of compound E. Let's go ahead and look at compound E. So compound E, we have 2.4 dimethyl pent 1-ene. So pent 5 carbons, 1, 2, 3, 4, 5. And then we have a double bond on the first carbon. We can tell from this pent 1-ene. So there we go. We have a double bond. And then on the second carbon, we have a branch with 1 carbon. And then on the fourth carbon, we also have another branch with 1 carbon. So now we're essentially done. We just left with filling out the hydrogens. So let's go ahead and do that. Yeah. So 1, 2, 3. We still need another hydrogen. And then 1, 2, 3. It's a painful exercise, but yeah, we have to do what we have to do. Compound A and B are functional isomers, like we are told in 3.1.1. What we are actually required to do is define the term functional isomer. Like all isomers, we have the same molecular formula, but in this case, the compounds differ by functional group. So the definition for functional isomer, same molecular formula, but different functional groups. Let's look at 3.1.2. Write down the IUPAC name of compound B. So the first thing you want to do is to determine which homologous series this compound B belongs to. Because of the structure of the functional group, compound B, it's a ketone. This carbon that is bonded to the oxygen is bonded to 2 other carbons. And because of that, we can conclude and say that compound B is a ketone. Now what we need is the longest carbon chain. Clearly, it is easy to see that this will be our longest carbon chain with 1, 2, 3, 4, 5 with 5 carbons. So we know we have pentane. We have pentane. Now what we need, or what we're looking for, is the position of the carbon that is bonded to the oxygen. If we start numbering from the left, we're going to have 1, 2, 3. If we start numbering from the right, we're going to have 1, 2, 3. So where we start numbering really doesn't matter. Our functional group is on the third carbon. So we're going to have pentane 3-one. That is the answer to 3.1.2. Let's look at 3.1.3. How does the boiling point of A compare to that of pentane 1-ol? So we have pentane 1 all, and compound A. Write down only greater than, equal to, or lower than. So let's go to compound A. Compound A is an aldehyde because the carbon that is bonded to the oxygen is only bonded to one other carbon. So that makes it an aldehyde. So we have pentane 1 all and pentanol. Pentane 1 all is an alcohol. So it consists of hydrogen bonding. We have hydrogen bonding in alcohols. And then pentanol is an aldehyde. It consists of dipole-dipole. So the intermolecular forces in pentanol is dipole-dipole. So in order to answer this question, you actually need to know which intermolecular force is generally stronger between hydrogen bonding and dipole-dipole. Compound A will have a lower than boiling point compared to pentane 1 all. Let me explain why that is the case in 3.1.4. The intermolecular forces in pentane 1 all, which happens to be hydrogen bonding, are stronger than the intermolecular forces in pentanol, which is dipole-dipole. And then you know that if you have stronger intermolecular forces, then more energy is required to overcome those intermolecular forces in that compound. And then as a consequence, the alcohol or pent 1 all will have a higher boiling point. That is the answer to 3.1.4. Let's look at 3.1.5. How will the vapor pressure of compound B compare to that of pentane 1 all? Right, only higher than, lower than, or equal to. Explain the answer fully. So compound B, like we've already deduced, is a ketone. And which intermolecular forces do we find in ketones? We have dipole forces. And then again in pentane 1 all we have hydrogen bonding. In pentane 1 all we have hydrogen bonding. So that will lead to ketone having a higher than vapor pressure compared to pentane 1 all. Higher than vapor pressure. So what you have to understand is that the weaker the intermolecular forces, then the higher the vapor pressure. So between compound B, our ketone, and pentane 1 all has stronger intermolecular forces. So it will require more energy to overcome the intermolecular forces. And then as a consequence, it is going to have a lower vapor pressure. It is going to have a lower vapor pressure compared to ketone. Ketone will actually have a higher vapor pressure. So what you need to memorize, or what you need to know, is that the stronger the intermolecular forces, the higher the boiling point, the higher the melting point, but the lower the vapor pressure. You need to know that. 3.2.1. Let's define the term boiling point. That is not the temperature at which liquid turns to gas. Please, we no longer use that definition at this level. It is actually the temperature at which the vapor pressure equals the atmospheric pressure. The temperature at which the vapor pressure equals the atmospheric pressure. That is boiling point. 3.2.2. Run down the independent variable for this investigation. Let's take a look at what is happening in this question. Let us use compound C to E to investigate one factor which influences the boiling points of organic compounds. What I'm realizing real quick is that in compound C we have 1, 2, 3, 4. We have 4 carbons, right? And then in compound D, we have 1, 2, 3, 4, 5. We have 5 carbons in compound D. And then in compound E, we have 1, 2, 3, 4, 5, 6. We have 6 carbons in compound E. So it seems like our independent variable here, what we are changing is actually the chain length. We can see that from the number of carbons we have in the compounds. So the answer to 3.2.2 would be chain length, or the molecular mass, because as the chain length increases, then the molecular mass is also going to increase. So that is the independent variable. And 3.2.3, write down the type of van der Waals force that occurs between these organic compounds. So these organic compounds are all alkanes, right? Well, you can draw compound C fairly quick by saying C 1, 2, 3 hydrogens, and then another carbon with 2 hydrogens, another carbon with 2 hydrogens, and the last carbon with 3 hydrogens. The same thing with compound D and E, they're all alkenes. So the force that is occurring in compound C, D, and E is actually London force. That is London force, or induced dipole forces. Well, let's look at 3.2.4. Write down the conclusion that can be drawn about the boiling point of straight chain alkanes. So let's look at our diagram. We can see fully well that as the number of carbon is increasing, our boiling point is increasing from -1 to 36.1 and lastly to 69. So we can conclude and say that as the chain length increases, the boiling point increases. If you had said molecular mass in 3.2.2, you would say that as the molecular mass increases, the boiling point increases. How can we boil down these complex concepts to a few bullet points? Well, if a reaction starts with an alkene and you get whatever product you're going to get, then that reaction is an addition reaction. If a reaction starts with whatsoever it is starting with and it ends up with an alkene, then that reaction is an elimination reaction. And if our first condition is not met and our second condition is not met, then that reaction is a substitution reaction. What am I even saying? Let me show you what I'm talking about by answering this question. Let's look at 4.1. Consider reaction A and write down the type of reaction that takes place. So reaction A is right here. So let me go through my conditions and see which one is met. Do we start with an alkene? No, we don't. We start with a secondary alcohol. Do we end up with an alkene? Yes, we do. We have propene as our product, right? So we know fully well that from that only, our reaction is an elimination reaction. Our second condition is met. So the answer to 4.1 is elimination. It's elimination. Just because we know that if a reaction ends with an alkene, it's elimination. If it starts with alkene, it's addition. And then if none of that is correct, then it is a substitution reaction. Let's do 4.2 and 4.2.1. Reaction B represents a hydration reaction. Let's look at B. At B, we're starting with propene and we end up with a secondary alcohol. And then we are told that that reaction is a hydration reaction. Right, and then now what we're asked to do is to define hydration reaction. It is the addition of water to a compound. That's it. That's the definition. It's the addition of water to a compound. That's what we mean when we talk about a hydration reaction. We add in H2O to a compound. And the follow-up question, 4.2.2, write down the name or formula of the catalyst used for this reaction. So a catalyst you can use for a hydration reaction is H2SO4. So we can use sulfuric acid as a catalyst for a hydration reaction. Let's look at 4.3 and 4.3.1. During reaction C, a specific rule is followed to determine the major product when HBr is added. Let's look at reaction C. So for reaction C, we are starting with propene and we end up with 2-bromopropene. So let's go back to our conditions. Do we start with an alkene? Yes, we do. So we know that reaction C is supposed to be an addition reaction. Well, the answer to 4.3.1 was actually very difficult to find. But if you visit the CAPS document and other relevant resources, you'll find out that for hydrohalogenation, our addition reaction in this case, we need no water because alkenes cannot react with pure water. And then apart from needing no water, we need a concentrated strong acid. So we need a concentrated strong acid for this reaction that we have in 4.3.1. It is an addition reaction
namely hydrohalogenation. We're adding a hydrogen and a halogen. 4.3.2, use structural formula and write down the balance equation for this reaction. So propene plus HBr. Let's go ahead and do that. So we're going to have 1, 2, 3 carbons, right? So 1, 2. Now we just need to add our hydrogens, and we're supposed to have something like that, plus HBr to give us something. If you look back to the equation statement, it says that during reaction C, a specific rule is followed to determine the major product when HBr is added. So now you actually have to know that rule in order to answer this question. Well, to some extent, we know that this double bond is going to break, and either one between H and Br is going to come to the second carbon, and then the other is going to come to the first carbon. So do we get Br on the second carbon, or do we get Br on the first carbon? You need to know where to place that Br, because if you place it at the wrong location, then you lose a mark. But there's a rule for that. There's a law for that. Markovnikov's rule. So basically what it is saying is that the hydrogen is going to go where there's a lot of hydrogens, and then the halogen is going to go to the other spot. So if you look at this carbon here, it has 2 hydrogens, and then the carbon in the middle has 1 hydrogen. So the hydrogen will tend to go to the carbon with a lot of hydrogens already. So that Br, it will usually go to the middle, because that's where we have the least number of hydrogen. So our product is going to look like this. Br is going to come to the carbon in the middle, and the hydrogen is going to come to the first carbon. And then now it's just a matter of filling out our hydrogens. So this is our major product according to Markovnikov's rule. And then Br being on the first carbon and H being on the second carbon is our minor product. This is our major product. Yeah, usually when this reaction occurs, this is the product, right? 4.1. Identify the type of reaction taking place at, so let's go to reaction D. Reaction D. Yeah, this one is going to be easy because we know our conditions. Do we start with an alkene? No. Do we end with an alkene? No. So we know that it is substitution. It is substitution. There isn't a lot to think about there. And then 4.2, which reaction are we interested in? We are interested in reaction F. In reaction F, do we start with an alkene? The answer is no. Do we end with an alkene? The answer is still no. So again, that is a substitution reaction. That is a substitution reaction. It cannot be otherwise. And then 4.5.1. Reaction E is a hydrogenation reaction. Let's look at reaction E real quick. We're starting with propene and we're ending up with propane. So it is indeed a hydrogenation, right? And then what does the equation say? Write down the 2 reaction conditions for this reaction. 2 reaction conditions for hydrogenation. So we need heat, and another thing we need is a catalyst. We need a catalyst. Yeah, which catalyst in this case? We need palladium, platinum, nickel, and so on. Right. And then 4.5.2, name one use of hydrogenation in the food industry. Well, I will leave that one to you.
This question is difficult, okay? But let's go ahead and give it a try. The first question, 3.1, we're supposed to define the term boiling point. So boiling point is the TP at which the VP is equals to the ATP, right? So the temperature at which the vapor pressure is equals to the atmospheric pressure. 3.1. Let's take a look at 3.2. In 3.2, write down the conclusion that can be made for curve P. So let's go ahead and read through our question statement and sort of figure out what is happening. So the relationship between boiling point and the molecular mass of aldehydes, carboxylic acids, and primary alcohols is investigated. Curves P, R, and S are obtained. All compounds used as straight chain molecules. Right. And then write down the conclusion that can be made for curve P. As we can clearly see, as the molecular mass increases, the boiling point is increasing. So that is the conclusion we can make for curve P. Well, the same is true for curve R, and the same is true for curve S. As the molecular mass increases, the boiling point also increases. Why is that the case? We're going to address that sometime later. That is 3.2. 3.3, explain the answer to question 3.2 in terms of the structures of the compounds. Okay, so now we actually have to support why we are saying that as the molecular mass increases, the boiling point increases. Well, not support, but justify why that is the case. So let's go ahead and try doing that. Okay, so when we're told that we have straight chain organic compounds, right? As the chain is increasing, the London forces are increasing. Okay, so that is the reason why when the molecular mass is increasing, the boiling point is increasing. It is because when you increase the number of carbons on your straight chain, the London forces are going to be increasing between those carbons. So that is the reason we're supposed to give for 3.3. I wrote it down. It says, as the chain length increases, the London force increases, and the boiling point will increase as a consequence because the intermolecular forces, the strength of the intermolecular forces is increasing. That is 3.3. 3.4, 3.4.1. Curve R represents alcohols. Well, we can deduce that curve R represent alcohols without being told. We can deduce that because we have an alcohol, we have a carboxylic acid, and we have aldehydes. We know which compounds consist of which intermolecular forces and which intermolecular forces are stronger than which. We know all that. So yeah, and they're telling us, but we already know. They don't have to. Okay, and then 3.4.1, which homologous series is represented by curve S. So we have aldehydes, carboxylic acids, and alcohols. We know that R is alcohol. Why is R alcohol? Because we have one side of hydrogen bonding, and S is aldehyde, right? Dipole forces. And P is carboxylic acid, where we have two sides of hydrogen bonding. Okay, so this is our acid, this is our carboxylic acid. What is the question saying? Which homologous series is represented by curve S? Aldehyde. Our homologous series is aldehyde. Aldehyde is the homologous series. Okay. 3.4.2. Explain the answer to question 3.4.1 by referring to the strength of intermolecular forces. So, okay, this is the train of thought. Between carboxylic acids consist of two sides of hydrogen bonding. Alcohol consists of one side of hydrogen bonding. Aldehydes consist of dipole, right? Hydrogen bonding is stronger than dipole. So for the same molecular mass, aldehyde should have the lowest boiling point compared to alcohols and carboxylic acids. So that is 3.4.2. Let's move ahead. Okay, we're moving up and not down. So we have 3.5. Let's take a look at 3.5 and hear the stories. 3.5.1, Write down the molecular mass of the compound with a boiling point of 97 degrees Celsius. For curve R, the molecular mass of the compound with a boiling point of 97 degrees Celsius. So let's go ahead and have a look. So here we have compound R. These are our boiling points on the y-axis. So let's go ahead and identify 97. 97 should be somewhere here, right? That's where we should have 97. And the molecular mass between 50 and 70, so that is 60. So the answer to 3.5.1, we have 60 grams per mole. 3.5.1. So a straight chain alcohol with a molecular mass of 60 grams per mole. Okay, so let's see. We have methanol. What else? We can also just write an equation for this. I think we can write an equation. Let's see. For an alcohol, we know fully well that we are supposed to have CnH2n plus 2O. Okay, this is the general formula of an alcohol. CnH2n plus 2O. We know that the molecular mass of carbon is 12. So we can say 12 multiplied by n plus that of hydrogen. So hydrogen, we have 2n plus 2. Okay, so we're going to have 2n plus 2 plus that of oxygen. Of oxygen, we have 16. Okay, this is equals to 60. So let's find the value of n in attempt to finding the alcohol with the molecular mass of 60. So we're going to have 12n plus 2n, that will be 14n. 2 plus 16, that is 18. This is equals to 60. So I have 14n being equals to 60 minus 18. 60 minus 18 should give us 42. So n is equals to 42 divided by 14. I think this is supposed to be 3. Okay, let me just verify if it is indeed 3. 4, 4, 4, 12, 2 plus 1, 42. So, right, n is equals to 3. So we know that our alcohol is C3H3 multiplied by 2, that is 6, plus 2, 8. So 3 C3H8O. This is propanol. This is propanol. So there we go. We have identified the alcohol. I'm sure there's other ways you can use to identify alcohol, but that is just, yeah, the approach I'm deciding to take. 3.5.2. 3.6. Two compounds A and B used in this investigation have a molecular mass of 74 grams per mole. A has a boiling point of 118 degrees Celsius and B a boiling point of 142 degrees Celsius. Explain the difference in these boiling points by referring to the structures of these compounds. Okay, so we're looking for two molecular mass, two compounds. Okay, so let's focus on compound A. Compound A has a molecular mass of 74 grams per mole, and then it has a boiling point of 118 degrees Celsius. So let's identify what A is first. Okay, so let's go to our graph. The molecular mass is 74. How many blocks do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have 10 blocks between 70 and 90. So 1, 2, 3, 4, 5 should give us 80. So we have 80 right here. So that tells me that, let me see. That tells me that 1, 2 should be 74. So if I want to find a molecule with a compound with a molecular mass of 74 grams, then I need to draw a line like that. So, okay, we have 74 grams per mole and a boiling point of 118. So, where can I find 118 here? Okay, I think I find it on the alcohol. Okay, let me erase here so that I can see what is underneath. I think I find it on the alcohol. This right here should have a boiling point of around 118. So compound A is an alcohol. I know that for sure. It cannot be compound. It cannot be S, because S is way below 100, and it cannot be P. It cannot be on the line P, because you can see it is very close to 150. So A is the alcohol. Let's take a look at B. What is the data I have for B? So B also has a molecular mass of 74 grams per mole and a boiling point of 142 degrees. Okay, so 142, we can clearly see that it is this one that we have up here, which is our acid. So B is the acid. So what does the question say? The question says, the question is up here. The question says, explain the difference in these boiling points by referring to the structure of these compounds. Okay, so we have the alcohol and the acid. In alcohols, we have one side of hydrogen bonding, while in an acid, we have two sides of hydrogen bonding. The intermolecular forces on the acid will be stronger than that on the alcohol, requiring more energy to overcome the intermolecular forces. And as a consequence, we're going to have a higher boiling point on compound B, the acid.
Compound A and B are functional isomers, like we are told in 3.1.1. What we are actually required to do is define the term functional isomer. Like all isomers, we have the same molecular formula, but in this case, the compounds differ by functional group. So the definition for functional isomer, same molecular formula, but different functional groups. Let's look at 3.1.2. Write down the IUPAC name of compound B. So the first thing you want to do is to determine which homologous series this compound B belongs to. Because of the structure of the functional group, compound B, it's a ketone. This carbon that is bonded to the oxygen is bonded to two other carbons, and because of that we can conclude and say that compound B is a ketone. Now what we need is the longest carbon chain. Clearly it is easy to see that this will be our longest carbon chain with 1, 2, 3, 4, 5, with 5 carbons. So we know we have pentane. We have pentane. Now what we need, or what we're looking for, is the position of the carbon that is bonded to the oxygen. If we start numbering from the left, we're going to have 1, 2, 3. If we start numbering from the right, we're going to have 1, 2, 3. So where we start numbering really doesn't matter. Our functional group is on the third carbon. So we're going to have pentane 3 own. That is the answer to 3.1.2. Let's look at 3.1.3. How does the boiling point of A compare to that of pentane 1-ol? So we have pentane 1-ol and compound A. Write down only greater than, equal to, or lower than. So let's go to compound A. Compound A is an aldehyde because the carbon that is bonded to the oxygen is only bonded to one other carbon. So that makes it an aldehyde. So we have pentane 1-ol and pentanol. Pentane 1-ol is an alcohol. So it consists of hydrogen bonding. We have hydrogen bonding in alcohols. And then pentanol is an aldehyde. It consists of dipole-dipole. So the intermolecular forces in pentanol is dipole-dipole. So in order to answer this question, you actually need to know which intermolecular force is generally stronger between hydrogen bonding and dipole-dipole. Compound A will have a lower than boiling point compared to pentane 1-ol. Let me explain why that is the case in 3.1.4. The intermolecular forces in pentane 1-ol, which happens to be hydrogen bonding, are stronger than the intermolecular forces in pentanol, which is dipole. And then you know that if you have stronger intermolecular forces, then more energy is required to overcome those intermolecular forces in that compound. And then as a consequence, the alcohol or pentanol will have a higher boiling point. That is the answer to 3.1.4. Let's look at 3.1.5. How will the vapor pressure of compound B compare to that of pentanol? That only higher than, lower than, or equal to. Explain the answer fully. So compound B, like we've already deduced, is a ketone. And which intermolecular forces do we find in ketones? We have dipole forces, and then again in pentanol we have hydrogen bonding. In pentanol we have hydrogen bonding, so that will lead to ketone having a higher than vapor pressure compared to pentanol, higher than vapor pressure. So what you have to understand is that the weaker the intermolecular forces, then the higher the vapor pressure. So between compound B, our ketone, and pentanol has stronger intermolecular forces, so it will require more energy to overcome the intermolecular forces, and then as a consequence it is going to have a lower vapor pressure. It is going to have a lower vapor pressure compared to ketone. Ketone will actually have a higher vapor pressure. So what you need to memorize, or what you need to know, is that the stronger the intermolecular forces, the higher the boiling point, the higher the melting point, but the lower the vapor pressure. You need to know that. 3.2.1. Let's define the term boiling point. That is not the temperature at which liquid turns to gas. Please, we no longer use that definition at this level. It is actually the temperature at which the vapor pressure equals the atmospheric pressure. The temperature at which the vapor pressure equals the atmospheric pressure. That is boiling point. 3.2.2. Run down the independent variable for this investigation. Let's take a look at what is happening in this question. Let us use compound C to E to investigate one factor which influences the boiling points of organic compounds. What I'm realizing real quick is that in compound C we have 1, 2, 3, 4. We have 4 carbons, right? And then in compound D we have 1, 2, 3, 4, 5. We have 5 carbons in compound D. And then in compound E we have 1, 2, 3, 4, 5, 6. We have 6 carbons in compound E. So it seems like our independent variable here, what we are changing is actually the chain length. We can see that from the number of carbons we have in the compounds. So the answer to 3.2.2 would be chain length, or the molecular mass, because as the chain length increases, then the molecular mass is also going to increase. So that is the independent variable. And 3.2.3, write down the type of van der Waals force that occurs between these organic compounds. So these organic compounds are all alkenes, right? Well, you can draw compound C fairly quick by saying C, 1, 2, 3 hydrogens, and then another carbon with 2 hydrogens, another carbon with 2 hydrogens, and the last carbon with 3 hydrogens. The same thing with compound D and E, they're all alkenes. So the force that is occurring in compound C, D, and E is actually London force. That is London force, or induced dipole forces. Well, let's look at 3.2.4. Write down the conclusion that can be drawn about the boiling point of straight chain alkenes. So let's look at our diagram. We can see fully well that as the number of carbon is increasing, our boiling point is increasing from -1 to 36.1 and lastly to 69. So we can conclude and say that as the chain length increases, the boiling point increases. If you had said molecular mass in 3.2.2, you would say that as the molecular mass increases, the boiling point increases.
The temperature at which the vapor pressure is equals to the atmospheric pressure is what we refer to as the boiling point, and that is 3.1. So from here on, let's go ahead and take a look at 3.1.2. What does the question say? Which of the compounds A, B, or C is mainly in the liquid phase at 100 degrees Celsius. My grade 10 learners can answer this question, but let's take a look and see what is happening. So we have organic compounds A, B, C, and D, but we are only concentrating on A, B, and C as our question instructs. So the question is, which compound of these three is mainly in the liquid phase at 100 degrees Celsius? Right, so it must not be a gas at 100 degrees Celsius. It must not have boiled at 100 degrees Celsius. So let's take a look. Compound A. The boiling point of compound A is 78 degrees Celsius. So at 100 degrees Celsius, we are above the boiling point of compound A. So it is already a gas at 100 degrees Celsius because it boils at 78. Same is true with compound B. Compound B has a boiling point of 46 degrees Celsius. So at 100 degrees Celsius, it is above its boiling point. So it has turned from liquid to gas already. So C is the compound that is in the liquid phase at 100 degrees Celsius. If we take a look at A, B, and C. So the answer here to 3.2, 3.2 and not 3.1.2. 3.2 is C. C is at the liquid phase at 100 degrees Celsius because it has not yet reached its boiling point. Okay, explain the difference in the boiling points of compound A and B. That is for 3 marks. So let's take a look at compound A and compound B and see how they differ. Well, they are all haloalkanes, but they differ in branching. The structure of compound A, let's take a look. 1, 2, 3, 1, 2, 1, 2, third carbon, fourth, 1, 2, and chloro. And then this is A. Let's take a look at B. Right. At B, we have 1, 2, carbon, hydrogen, 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 and then hydrogen. Well, let's just leave the dash there. And then we have another carbon that serves as a branch. And then carbon, hydrogen, hydrogen, chloro. So this is compound B. As you can see, in compound B, we have this branch here. And then in compound A, we don't have a branch. So the difference in the boiling points of compound A and B is because compound A is less branched compared to compound B. So compound A is going to have more surface area, stronger intermolecular forces, and thus more energy is required to overcome the intermolecular forces in compound A. That is why we see a higher boiling point compared to compound B, because it is less branched. Okay, so that is 3.3. What about 3.4 and 3.4.1? Let's go ahead and take a look. Consider the boiling points 75 degrees Celsius, 120 degrees Celsius, and 126 degrees Celsius. Which of these values represents X, the boiling point of compound D? So let's go ahead and take a look at compound D and see if we can make sense of this. Compound D seems to be an aldehyde. Let's take a look. Carbon, 3 hydrogens, carbon, 2 hydrogens, carbon, 2 hydrogens, carbon, oxygen, 1 hydrogen. So compound D is indeed a aldehyde, but compound C is an alcohol. Right, so the boiling point of compound D must be lower than that of C, because aldehydes we have dipole, and then in alcohol we have hydrogen bonding, and hydrogen bonding is way stronger than dipole. So X should be less than 118 degrees Celsius at least. So take a look at this. We have 120. So this can't be correct because D must have a lower boiling point compared to C, because D is dipole and C is hydrogen bonding. And then this is also not true because it cannot be higher than that of alcohol. So the only thing that makes sense is 75 degrees Celsius. So 3.4.2, we have 75 degrees Celsius. So X makes sense to be 75 degrees Celsius. Well, 3.4.2 says explain, and we've explained that. Now let's take a look at 3.5. 3.5 is quite an interesting one. I had to take some time and think about that. The atmospheric pressure is now changed to 83 kilopascals. Well, under normal circumstances, we have 101 kilopixels. I think 101.3, something like that. But I know for sure it is around 101. And now it has changed to 83 kilopixels. Now it is changed to 83 kilopixels. Let's hear the stories. How will the boiling points of these organic compounds be affected? Choose from increase, decrease, or remain the same. So do the boiling points increase, decrease, or remain the same if we lower the vapor pressure? Well, let's stick to the definition. What is boiling point? Boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. So you are essentially increasing the vapor pressure so that it reaches the atmospheric pressure, and we say that we have reached the boiling point. Essentially, if you are lowering the atmospheric pressure, you will reach a boiling point way sooner than you would under normal circumstances. Right, maybe for water, the boiling point is 100 degrees Celsius. So if you lower the atmospheric pressure, you would reach the boiling point, let's say at 80 degrees Celsius, way before what it usually is at 101 kilopixels. So this would actually make the boiling point to decrease. Right, this is the first time I'm actually coming across a question like this, but I'm quite convinced that decrease is our answer in the 3.5. If you have any other ideas, just let me know in the comments and let's talk about it. Apart from that, which video do you want me to do next? Pressure exerted by vapor at equilibrium with its liquid in a closed system. That is vapor pressure. 3.2. Which one of the compounds A or B has the higher vapor pressure? So what do we know? We know that the higher the boiling point, the higher the melting point, the higher the viscosity, but the lower the vapor pressure. So which one of the compounds A or B has the higher vapor pressure? Well, the compound with the lowest boiling point will have the highest vapor pressure. So between A and B, which one has the lowest boiling point? It is compound A with minus 42 degrees Celsius. Compound B has a boiling point of 36 degrees Celsius. So the answer here is A. A has the lowest boiling point, so it should have the highest vapor pressure. Right, 3.3.1. Let's consider compound C, 2-methylbutane. Is compound C a saturated or unsaturated hydrocarbon? Well, it is easy to see that it is saturated. Why are we saying that it is saturated? A compound is saturated if it only consists of single bonds between the carbon atoms, no multiple bonds whatsoever. That is a saturated compound. Just like our compound C, it is a simple alkene, saturated compound. Alkene and alkynes are unsaturated because we have double and triple bonds. Here we only have single bonds. 3.3 because we've just answered 3.3.2 there. Which type of intermolecular forces are mainly present between these compounds? Well, the compounds on our table, we have propane, pentane, 2-methylbutane, and then we have an outlier, pentane 1-ol. As you can see, one intermolecular force that is present from compound A to compound D is London forces. It is present even in compound D, pentan 1-ol. So that is the type of intermolecular force which is mainly present between these molecules. There is London forces in pentan 1-ol. It is just that the strongest intermolecular forces in pentan 1-ol will be hydrogen bonding, but London forces is present. 3.3.3. Let's go ahead and look at 3.4.1 and 3.4.2. Define the term structural isomer. Organic compounds with the same molecular formula but different structural formula. Same molecular formula but different structural formula. Just like compound B and C, we have C5H12, 3.4.2 refer to the structure intermolecular forces and energy in your explanation to explain why compound B has a higher boiling point than compound. Let's go ahead and have a sketch of compound B. 5 carbons in a straight line. So 1, 2, 3, 4, 5. While compound C on the other hand, we have 1, 2, 3, 4, and a branch on the second carbon. How does compound B differ from compound C? The only difference between these two compounds is the degree of branching. Compound B is less branched compared to compound C. Less branched means more surface area. So we have more surface area in compound B. From there on, our song starts. More surface area, stronger intermolecular forces. If the intermolecular forces are stronger, more energy will be required to overcome the intermolecular forces, and consequently a higher boiling point, just like we can see. Right, so B is less branched compared to compound C, as we can clearly see. This is straight, and here we have a branched. Less branched will mean more surface area. More surface area, stronger intermolecular forces, more energy is required to overcome those intermolecular forces. I hope that is clear. The last question, 3.5, explain the difference in the boiling points of B and D. Refer to the intermolecular forces and energy in your explanation. Let's go ahead and look at B and D. B is pentane and D is pentane 1-ol. Look at the difference in the boiling point, even though they have the same number of carbons, 36 degrees Celsius and 137 degrees Celsius. So why does compound D has a higher boiling point compared to compound B? Well, compound B consists of London forces, while compound D consists of hydrogen bonding. We know fully well that hydrogen bonding is a stronger intermolecular force compared to London forces. So compound D will have stronger intermolecular forces. More energy will be required to overcome the intermolecular forces in compound D, and as a consequence, it has a higher boiling point.
If a reaction starts with an alkene, then it is an addition reaction. And then if it ends with an alkene, it is an elimination reaction. And if the first condition or the second conditions are not met, then it is a substitution reaction. So this is how you can easily identify the type of a reaction by just looking at the compound it starts with or the product that you have. If it starts with an alkene, it is an addition reaction. If it ends with an alkene, it is an elimination reaction. And if either of those are not true, it is a substitution reaction. So let's see how we can use this to answer this question. So 4.1.1, identify the type of reaction represented by B. So take a look at reaction B. Does it start with an alkene? No, it does not. It starts with an alcohol. So it cannot be an addition reaction. Does it end with an alkene? Yes, it does. As soon as we see that, we know that it is an elimination reaction because it ends with an alkene. Right, those are the only two things we need to look at. If it didn't end with an alkene, then it would be a substitution reaction. That is 4.1.1. Let's take a look at 4.1.2. Identify the type of reaction represented by D. So again, does it start with an alkene? No, it does not. Bromoethane is not an alkene. And does it end with an alkene? It is not. It ends with an alcohol. So because the first condition is not met and the second condition is also not met, then we are saying that it will be a substitution reaction. Those are the only two things that we need to look at. Does it start with an alkene? Does it end with an alkene? If that's not the case, then it is a substitution reaction. So there we go. That is 4.1. Let's take a look at 4.2. 4.2, we're supposed to write down two reaction conditions for reaction B. So reaction B it's easy to see that we have a elimination reaction. So heat is a reaction condition for all elimination reactions. Heat is a reaction condition for all elimination reactions. Right, so heat is our first answer, right? As soon as we see a reaction condition and it is elimination, heat, we're going to think after that. So now let's find another reaction condition. So what is happening here? We have dehydration, right? We have an alcohol turning to an alkene. So we need a dehydrating agent, of which we can use a catalyst such as H2SO4. So we also need a catalyst as a reaction condition for this elimination reaction that we have. 4.2, let's take a look at 4.3 and 4.3.1. For reaction A, write down the name of the inorganic reactant. So reaction A, we are turning an alkene into an alcohol. Obviously, we need H2O to turn an alkene into an alcohol. And by our definition, H2O is inorganic because it does not contain carbon. So name of the inorganic reactant, it is water, right? Not H2O. The question is very specific. We are looking for the name of the inorganic reactant. And then 4.3.2, chemical formula of the catalyst used. Chemical formula, not the name, right? So don't confuse the two. Well, you know what they mean. Just be careful and not write a formula when they want a name, or write a name when they're looking for a formula. So here the chemical formula of a catalyst needed. We need H2SO4. Right. H2SO4 is not always the answer to equation with regards to catalyst. Right. It just happens that we have used it twice in this equation. Okay. 4.4. 4.4.1. Let's take a look. For reaction C. Okay. So reaction C, we are turning an alkene to a haloalkane. Right. And then 4.4.1, use structural formula and write down a balanced equation. Okay, we're supposed to use structural formula. So this is our alkene with 2 carbons. How many bonds do we have? 1, 2, 3. So we need another hydrogen. And we can see that our product is bromoethane. So what are we adding here? We're adding HBr. And this should give us bromoethane. So the double bond gets broken, and it's just a matter of filling out the hydrogen and the bromo in one of those bonds. So there we go. I don't think there's any wrongdoing that we do in there. I think all is well, right? Quite an easy reaction. We have our alkene. We add a hydrogen and a halogen, so it is a hydrohalogenation addition reaction, and then this is our product. Okay, there we go. 4.4.1. Let's take a look at 4.4.2. So 4.4.2, explain why no water should be present during this reaction. Explain why no water should be present during this reaction. We are avoiding the formation of OH instead, right? If you have water, it's very possible that instead of having Br there, you might have OH. So that is what we are running from. Yes, we are trying to avoid the formation of the hydroxyl group, right? That is 4.4.2. 4.5, let's go ahead and take a look. So we are now concentrating on reaction E. Okay, let's see what the first question says. Type of reaction. Okay, so reaction E represents the conversion of the alcohol into organic compound X. So reaction E. Okay, so we start with an alcohol, as we can clearly see, and then we add what looks like an acid to get compound X. So something should come to mind when we talk about alcohol plus acid. This is clearly a esterification. So the answer to 4.5.1 is esterification. An alcohol plus an acid in the presence of a suitable catalyst will give you esterification, right? It will give you an ester. So type of reaction, esterification, right? So esterification. There we go. That is 4.5.1. Let's take a look at 4.5.2. Chemical formula of the catalyst used. We know what suitable catalyst we need in esterification. We need concentrated H2SO4. That's what we use in our esterification reactions. And then 4.5.3, structural formula of compound X. Compound X, I would assume, is the product formed. Let's go ahead and take a look. Okay, there we go. So our alcohol has 2 carbons. 1, 2. Okay, that's easy to see. And then our acid, let's go ahead and find out. We have 1, 2, 5, right? That's C multiplied by 3 there. So we have 1, 2 from the alcohol, and then we still have our oxygen from the alcohol. And then as long as it comes, and the carboxylic acid, we still have our double bond oxygen. And then 1, 2, 3, 4. So in total, 1, 2, 3, 4, 5. We have our 5 carbons from the carboxylic acid. So now, what we just need to do is to fill out the hydrogens everywhere else. I hope we're looking for the structure of the product and not the entire reaction, right? So there we go. Yes, maybe we should just do the reaction, the entire reaction, so that you can see where it is coming from, right? Maybe we should do the entire thing so that you can see where it is coming from. But this is the answer. This is our product. This is compound X, right? Let me show you where it is coming from. Either way, let me show you where it is coming from. So we're saying that our alcohol has 2 carbons. Yes, so it means that we have 1, 2, OH, hydrogen, hydrogen everywhere else. Okay, this is what we have, plus the carboxylic acid. Our carboxylic acid has 5 carbons, so it is 1, 2, 3, 4, 5. Well, let me put these a little bit to the right so that it will be easy to see when we remove our H2O, so that it can be easy to see when we remove our H2O. So hydrogen everywhere else. Hydrogen everywhere else. Okay. There we go. So what happens is that the alcohol loses the hydrogen and the acid loses the OH. Okay. And then that is why a byproduct or an inorganic product of esterification is H2O. Right. So we essentially losing this. We'll lose this part because water is removed from, well, we get water when we add the two compounds. So that is why our product ends up looking like this. This is why our product ends up looking like that. Okay, so there we go. I hope you can see where it is coming from. Right, the alcohol loses a hydrogen and the carboxylic acid loses an OH. But anyway, stories. Let's take a look at the question that follows. Is it 4.5.4? I think so. We're looking for the IUPAC name of the compound. So how do we name an ester? Right, well, we started with the alcohol and then we finished off with the acid. So the alcohol here is ethanol, as it has 2 carbons. So we're going to have ethyl, and then the carboxylic acid is pentanoic acid, as we have 5 carbons. So we're going to have pentanoid. So the name of this ester is ethyl pentanoid. Right. If the alcohol had 3 carbons, it would be propyl pentanoid. If the carboxylic acid had 4 carbons, for instance, it would be ethyl butanoate. That is how it works. First part of the name comes from the alcohol, how many carbons we have, and the second part of the name comes from the acid, how many carbons we have. That is 4.5, 4.6. Let's go ahead and take a look. So 4.6, reaction F takes place in the presence of warm concentrated sodium hydroxide. Use condensed structural formula and write down a balance equation for this reaction. Let's go ahead and take a look at reaction F. So reaction F, bromoethane to give us an alkene. Okay, so let's take a look there. In the presence of concentrated NaOH. So in the presence of concentrated NaOH, that's where elimination is going to take place. If it was in the presence of dilute NaOH, then substitution would take place. So let's go ahead and take a look at that. We start off with our bromoethane. Okay, so Br, hydrogens everywhere else. Okay, this is what we're starting with. And then plus NaOH. Okay, so what happens here is that, well, we are supposed to use condensed structural formula, not the way I'm doing it here. But let me just carry on with this for the sake of clarity. After doing this, then we're going to write it in the correct form. We're going to use condensed structural formula. Okay, so let's just carry on with this for the time being. So what happens here is that Na will bond with Br, and then OH will bond with the hydrogen removed, right? And then it means that our product, well, our byproducts, we're going to have NaBr plus H2O. Okay, that's how it goes. So let me show you. It means here that the products, we're going to have one double bond because now it is an alkene, hydrogens elsewhere, plus NaBr plus H2O. This is how the reaction takes place in terms of the structural formula. But our equation, we're supposed to use condensed structural formula. So let's go ahead and do that. This is just for the sake of clarity. So condensed structural formula, CH3, CH2Br. Okay, plus NaOH. And what does this give us? This gives us CH2, CH2. As you can clearly see, CH2, CH2. And then plus NaBr plus not NaOH, but H2O. Right, we have H2O there. So there we go. That is the condensed structural formula for reaction F. Okay, so 4.7, cracking. Let's take a look. We know fully well that this is still part of our syllabus, but it's one of those questions that they're not usually there in the exam. But let's go ahead and take a look at it. A large straight chained alkenes can be catalytically cracked to produce shorter chained alkenes and branched alkanes, which are more suitable for use in petrol. The reaction below indicates the catalytic cracking of octane. Okay, so octane, obviously we are expecting 8 carbons, and then here on the alkene we have 2 carbons. It means that on compound Y, which should be an alkene, we should have 6 carbons. So C6H14. That's what we expect compound Y to be. Right. So what does the question say? Write down the IUPAC name of compound Y. So 6,6, that is hex. So this is hexane. 4.7.1 is hexane. So there we go, hexane. And then 4.7.2, briefly explain why shorter chain alkenes and branched alkanes are more suitable for use in petrol than larger straight chain alkanes. So what do you think it is the answer to this question? Explain why shorter chain alkenes and branched alkanes are more suitable for use in petrol than larger straight chain alkanes. Right, maybe just to give you a hint, think about intermolecular forces, energy required, so on and so on. Let me know in the comments what your answer to this question is.
The name or formula of the catalyst used. So let's go ahead and take a look and see what is happening. In an experiment, a test tube containing methanol, propanolic acid, and a catalyst is heated in a warm bath. Well, we have the setup in front of us. The warm bath. Under the warm bath, we have some heat, methanol, propanolic acid, and a catalyst. Already, you should be able to tell that we have esterification taking place. Okay, so which catalyst is required when we are trying to have esterification? The catalyst is H2SO4. That is the catalyst. The question says name or formula. So if you say sulfuric acid, that would also be fine. But in some instances, the question would say the name, and then if you write H2SO4, it would be wrong, or it says the formula, of which if you write the name, it would be wrong. Right, so there we go. That is 4.1.1. What about 4.1.2? The type of reaction taking place. Even in, say, after doing all the questions, what does this comment say? Do you mind doing multiple choice for paper 2? We'll see about that, but I doubt I will. Multiple choice takes too much time and it doesn't get as much views, so it doesn't make sense for me to do it. The type of reaction taking place is esterification. So esterification, there we go. That is 4.1.2. And then 4.1.3, 2 reasons why the use of a water bath is preferred in this experiment over direct heat. One of the reasons is because alcohol is extremely flammable, right? So there we go. That is one reason. Alcohol is flammable. So if you put it on heat, if you put it directly on heat, then it's gonna burn, and that's not what we want. So that is one reason why we use a water bath over putting the reactions on heat themselves. So what is the other reason? I would like you guys to tell me. So please leave a comment and tell me which other reason you can think of. Well, in class, during the course of the year, at the beginning of the year, we actually performed this experiment, and we lost patience at some point of time because it was taking too long, and we put the test tube directly on heat, on the fire that was burning. Yeah, because we're using a sort of a Bunsen burner. I forgot the technical name of the apparatus we were using, and then we experienced some issues. Well, almost all the contents evaporated from the test tube, so we were not actually able to smell the contents, or because after an esterification you take a smell and then there's some things that you write, so on and so on. So we're not able to do that because we lost patience and put the test tube over the fire. But let me know, which other reason can you think of? That is 4.1.3. Let's do 4.1.4. The balance equation for this reaction using structural formula. So we have methanol plus propanolic acid. So let's go ahead and take a look. Methanol, so alcohol with 1 carbon. Okay, that is methanol. Plus propanolic acid, acid with 3 carbons. So we're gonna have, let's take a look. Carbon, well, we're supposed to have OH here, and let's see. Oh, we need more space. Let me start with the H instead. H, O, carbon double bond oxygen, right? And then let's 3 carbons and not 2 because it's prop. So hydrogen, and we need another hydrogen here. 1, 2, 3, 4. Okay, so this hydrogen, that carbon is fine, and then this will give us an ester. So what's gonna happen? The alcohol loses the hydrogen and the acid loses the OH. As a result, we're gonna have carbon, oxygen, and then now carbon. Okay, and then 1, 2, 3. Okay, there we go. And then now we just need to fill out the hydrogens, right? So let's do that. So there we go. We're supposed to have something like this, and then obviously here we can write H2SO4 as our catalyst. But what happened to the H2O that we removed is that it doesn't disappear. So we're gonna have plus oxygen HH, not plus H2O, because H2O is not a structural formula, right? You're supposed to write it in this manner. If you write it as H2O, that is technically wrong because H2O is not a structural formula. So this is what we have. Let me just check and see if I'm not making any mistake. Okay, let me take a look. I'm supposed to have an oxygen here and not hydrogen. 1, 2, 3, 4, 5. Okay, another mistake. Hydrogen. I've removed that hydrogen. It's all going well now. I think I have everything covered now. So that is 4.1.4. I hope you didn't make those mistakes that I was making there. The IUPAC name of the organic product for this reaction. The organic product is the ester and not the H2O. So what is the name of this ester? We're gonna have methyl propanoate, right? This part of the name comes from the alcohol and this part of the name comes from the acid, methyl propanoate. Right, I think we have that covered. Let's take a look at 4.2. Compound A is a 6-carbon branch alkane and it is used in a 2-step reaction to prepare compound C. Okay, so compound A, and then we go to B, and lastly we go to C. Reaction 2 is an addition reaction. If reaction 2 is an addition reaction, then here we have an alkene because you can only add it to an alkene. Okay, we know that for sure. And then 4.2.1, the name or formula of the inorganic reactant needed in reaction 2. So we have an alkene and our product is an alkane. So we have an alkene and our product is an alkane. So I think, it is quite easy to deduce here that we have a hydrogenation. We have a hydrogenation. So what is the inorganic reaction needed for hydrogenation? Platinum, palladium, nickel. I wonder what else, but those are the ones that I can recall from my head on the spot. Okay, 4.2.2, the IUPAC name of compound B. So compound B is an alkene. Let's try sketching the alkene. We can try sketching the alkene using compound C. We're sort of removing 2 hydrogens there. So the question says the IUPAC name, but it's better to sketch before we actually name the compound, right? It becomes easier. So let's see. 1, okay, and then carbon, and then carbon, and then here we're gonna have carbon and then another carbon, but we are removing 2 hydrogens in reaction 1, right? Not 2 hydrogens, but let's say, yeah, we are removing the compound that is here and another compound, not compound but element, another element that is there, right? So we have a double bond here as a consequence. In compound B we have a double bond because how are we adding these 2 hydrogens in reaction 2 if compound B doesn't have a double bond? It will not make sense. So we have a double bond there. So now we can name compound B using that knowledge. So if we're to name compound B, obviously we would have butane 1 in, okay? And then so this is 1, 2, 3, 4. So on the 3rd carbon we have 2 not 2 because like I said on the 3rd. So why do I say on the 3rd and say 2? Right, let me just, I'm trying to drag this to the right. So I'm gonna have 2.2 dash dimethyl butane 1 in. So let me hide the structure and try drawing it and see if I'm going to end up with the same thing. So butane, so 1, 2, 3, 4. 1 in, double bond. 2.2 dimethyl. So 2 is here. So carbon, carbon. Is that what we have? Is that what we're dealing with? That is not quite what we are dealing with. Because if I reveal that structure, let me do that. I have, okay, the carbons are on the third. So this is 3.3 and not 2.2. Right. If I didn't do that, if I didn't try to verify, I was actually going to get it wrong. So yeah, I'm glad I did try to verify because I had made a mistake. But anyway, stories. That's what we have. That is 4.2.2. And then what about 4.2.3? The type of reaction represented by reaction 1. In reaction 1, we have a haloalkane. Oh, well, in compound A, in reaction 1, we start with a haloalkane and we end up with an alkene. Clearly, it is an elimination reaction. Yeah, because we start with a saturated compound and we end up with an unsaturated compound. So that is 4.2.3. Using structural formulas, write down a balanced equation for reaction 1. Let's go ahead and take a look at reaction 1. We are starting with but1 in. We are adding a hydrogen and a halogen to get some product X. Well, in our previous videos, I've made it very clear. If a reaction starts with an alkene, it is an addition reaction. Without looking at any other thing, if it starts with an alkene, it is an addition reaction. No questions asked. What are we adding in this reaction? We're adding a hydrogen and a halogen. Well, let's start and see what we're going to have. We are starting with but1 in. So that is 1, 2, 3, 4. And on the first carbon, we have a double bond. So now it's just a matter of filling out the hydrogens. Let's go ahead and do that and see where we end up. Right, there we go. We have but1 in. Let's make sure that we have the correct number of hydrogens. On this carbon, we have 1, 2, 3, 4 bonds. So that is okay. On the second carbon, we have 1, 2, 3, 4. So it seems like everything checks out. So what are we adding? We add in a hydrogen and a halogen. The name of this addition reaction would be hydrohalogenation. The name of an addition reaction comes from what you are adding. Well, let's go ahead and have our products. It is easy to see that this double bond is going to break to accommodate the hydrogen and the halogen. But where is the hydrogen going to go? Where is the halogen going to go? The hydrogen is going to go to the carbon with the most number of hydrogens already. If you look at our situation, this first carbon here has 2 hydrogens and the second one has 1 hydrogen. So the hydrogen is going to go to the carbon with the most number of hydrogens. That is Markovnikov's law. So let's go ahead and have our product now. We're saying that our hydrogen is going to go to the first carbon as it has the highest number of carbons compared to the other carbon that it can possibly occupy. Yeah, so from this reaction, this is our major product. Our minor product is when the halogen is on the first carbon. That is 4.1 marks. Let's go ahead and do 4.2. Write down the name of the type of reaction that occurs when but1 in is converted to compound X. We already know that if a reaction starts with an alkene, we have an addition reaction. Quite an easy question to answer. 4.3. Write the structural formula and IUPAC name of the secondary alcohol Y that forms. So we've but1 in, and through some reaction 3, our product is a secondary alcohol. Well, it is starting with an alkene, so we know that it is an addition reaction. Which addition reaction leads to an alcohol hydration, right? Also given that it is a secondary alcohol, but we would also be able to get to a conclusion that the alcohol that is formed is secondary. But anyway, let's go ahead and have our alcohol. 1, 2, 3, 4. On the second carbon, we have OH. Yeah, that is wrong. It's not supposed to be like that. We're supposed to have a dash here to show that OH is not one thing. It is an oxygen bonded to a hydrogen. If you are writing the structural formula, you need to put that bond there. Well, everywhere else we have hydrogens. So we can just go ahead and put that there. Again, our product is a secondary alcohol because of the Markovnikov's law. Let's go ahead and name this alcohol. How many carbons? 1, 2, 3, 4. Which side are we numbering from? From the right, because our OH is going to be on the second carbon. But if we start numbering from the left, it is going to be on the third carbon. Well, it means that our IUPAC name will be butane-2-ol, right? The functional group is on the second carbon. That is 4.3. Let's do 4.4. Name the type of substitution reaction that occurs when compound X is converted to the secondary alcohol Y. So there is only one substitution reaction that can give you an alcohol. It is hydrolysis. There is no other substitution reaction that leads to the formation of an alcohol. So without thinking very hard, we know that the answer is hydrolysis there. If your alcohol is formed through a substitution reaction, it is hydrolysis. If it is formed through an addition reaction, it is hydration. Yes, 4.5, 4.5.1. Butane can be converted directly to the secondary alcohol without the formation of the intermediate product X with the help of a catalyst. 4.5.1. Except butane, write the name of the reactant needed for this reaction. Well, a reaction that takes us from butane to the secondary alcohol, it is an addition reaction. But they don't want to say now in 4.5.1 because it is equation in 4.2. So if they tell you what it is, then you can actually say, oh, okay, it means that the answer to 4.2 is addition. What do you need to add to butane in order to have an alcohol as your product? You need to add H2O, but they say the name. So if you write H2O, it is wrong because H2O is not the name. The name is water, right? That is another trick to the question, because if you write H2O, I'm telling you, your answer is wrong. You need to write water. And 4.52, write down 4.5.2, write down the formula of the catalyst that can be used. If you write sulfuric acid, your answer is wrong. The question says formula, so you're supposed to write H2SO4 and 4.5.3. Name the type of reaction that will occur during this direct conversion. It's 2 marks for one question because the same question is getting asked in 4.2. The type of reaction that will occur is addition.
Which letter represents an alkene, right? So what we want to do here is to have a functional group of an alkene, right? So we know that in an alkene, we have a double bond, right? And then the name ends as E-N-E. So when we go to our table here, whatever that has a double bond or the name ends with E-N-E, we know fully well that that's an alkene, right? Clearly on A here, we have a double bond. So as soon as we see that there's a double bond, we know that it's an alkene, right? So right now we can just write A. And then B, we don't have any double bond between carbon atoms. And then on C, we have a double bond here. So C is part of our solution. So for 2.1.1, we have A and C. And then for D, there's no double bond, and then it doesn't end with E and E. And then for E, no double bond, and then for F, there's a triple bond, right? And that's not what we're looking for. So the answer for 2.1.1, we just have A and C. Now let's go to 2.1.2, which letter represents a ketone. Again, we're going to look at the functional group of a ketone. For a ketone, we need something like this, right? We need a carbon that is bonded to an oxygen and then bonded to two other carbons, right? So if we see something like that, or a name that ends with O-N-E, then we know that we have a ketone, right? So for A, we already know that A is an alkene, so there's no way it can be part of our solution. But then if you look at B, we have a carbon here bonded to an oxygen and two other carbons. So clearly B is our ketone, right? So for 2.1.2, we have B. C is also an alkene, so it cannot be part of our solution. D doesn't have what we're requiring. E and F also doesn't have what we're requiring. So now we can go to 2.1.3. 2.1.3 says, let's look for a compound with a general formula CnH2n-2, right? If you're not already familiar with this, this is an alkyne, right? The name ends with Y-N-E. Another way of identifying it, we have triple bonds, right? So a carbon is bonded to another carbon, and there's triple bonds in between the two. So again, we go to our table and we look for that. A cannot be part of our solution. B cannot be a part of the solution. C also cannot be part of our solution, right? And then D, we don't have a triple bond or Y-N-E, right? So that cannot be part of our solution. For E, no triple bond. And then F, that's where we have our triple bond, right? You can see it here. So for 2.1.3, we can put F as our answer, right? The way of approaching this problem, you have to know exactly what you're looking for, right? It becomes extremely easy when you do that. And then 2.1.4 says, let's look for a structural isomer of octanoic acid, right? Octanoic acid. So for an acid, if we're looking for a structural isomer, we're looking for another acid, or we're looking for an ester, right? Because acids and esters are functional isomers. So if the structural isomer is an acid, then we should find something of this manner, right? Or something that ends with the name acid, right? And then if it's an ester, then we're looking for something like this, right? Or a name that ends with ATE, right? A cannot be part of our solution, B cannot be part of our solution, C cannot be part of our solution. But obviously, if you look at D, this name here ends with ATE, right? And then not only does it end with ATE, it also has 8 carbons, right? Like the octanoic acid, which is of our interest, right? So the answer of 2.1.4, we are going with D. And then now we can do 2.2. 2.2 starts by saying that let's write down the UPEC name of compound A. So what you want to do first, step number 1, is that to identify the longest carbon chain, right? So we have 1, 2, 3, 4, 5, 6. Even if you take any other way, you'll end up with 6, right? So now we know that as part of our name, we should have hex. Now we are going to look for the side which leads us to the functional group first. Obviously, if we start counting from this side, if we say 1 here, 2 here, and then we have our functional group, right? So it will say hex 2 in, right? But then if you start on the other side, you'll say 1, 2, 3, 4, and then it will be on carbon number 4, right? So we prioritize the side that leads us to the functional group first. So we have hex 2 in, right? Now we can look for the branches. So let's name our carbons first. So that is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6, right? On carbon number 4, we have a branch. We have one carbon, right? And then on carbon number 5, we also have a branch. So now we can say 4,5 dash. We don't say methyl, right? Because we have 2. Instead of saying methyl, we say dimethyl. 4,5 dash methyl, right? And between words, there's no need to put a dash. Now we can go and do 2.2. We need the UPEC name of compound E. So let's go look at compound E. Let's look for the longest carbon chain. So if we say this is 1, 2, 3, 4, 5, 6, 7, and then if we take this way and we keep going forward, we get 6, right? So we can conclude that the longest carbon chain has 7 carbons. So what is 7? We know fully well that 7 is hept, right? So we have hept. And then let's look for the functional group. It's an alkane, right? Every carbon is essentially the functional group. So we don't put anything there for an alkane. We can just say heptane. You only put something when you have an alkene or you have an alkyne. And then all the other complicated organic compounds with other functional groups. Now you will realize that we have an ambiguity here. We have a halogen on the second carbon, right? When you start counting from the left, and then we have a branch on the third carbon when you start counting from the right? So which one do we prioritize between the carbon and the halogen? Between the carbon and the halogen, we prioritize neither. So whatever that comes first, it's what we take, right? If a certain path gives us methyl first, then we're going to take methyl. But then if we start counting from the left, then we get to bromo first. So we're going to take bromo, right? But then you can get a situation where on the left path, you get to bromo, and then on the right path, you get methyl. What do you do when you have a situation like that? Then you have to check the alphabet, right? You have bromo and methyl. So you would take bromo because alphabetically wise, bromo comes first. But then now, because bromo is on the second carbon from the left, and then the methyl is on the third carbon from the right, you just take bromo automatically. And then if the methyl was on the second carbon and the bromo was on the third carbon, then you would take the path that leads to the methyl first. So we have carbon 1, 2, 3. So on carbon 2 and 3, we have 2 halogens, right? So we're going to have 2,3 dash dibromo, right? Because we have 2. And then we can then look for the branch, right? Carbon number 4, carbon number 5, and then on carbon number 5, we have methyl, right? So we're going to have dash 5 dash methyl. And then there goes our UPEC name. And then last but not least, we have 2.23, which says let's write the UPEC name of compound F. In compound F, we have an alkyne, right? Because we have an alkyne, we have a functional group. So naming will be much easier because we always prioritize the functional group. So we're going to start naming from this carbon here. So we're going to have 1, 2, right? And then 3, 4, 5. Even if you go up, you still have 5 carbons, right? So now it's easy to see that we'll have pent, right? And then now let's look for the position of the functional group on the second carbon. So we're going to have pent 2YNE. Now we can look at the branches and so on. We have a branch on the fourth carbon. So we're going to have 4-methyl. Now let's do 2.3. So 2.3 says that compound D is prepared by reacting 2 organic compounds in the presence of an acid as a catalyst. And then 2.3.1, let's write down the structural formula of compound D. So let's go and look at compound D. So compound D is pentyl propanoate, right? We know that if it ends with propanoate, It's an ester, right? One thing about an ester, the first part of the name is the alcohol, and the last part of the name is the acid. So let's write the structural formula. We know fully well that pent is 5, right? So we're gonna have 1, 2, 3, 4, 5. We're saying that the first part is the alcohol, right? So here we were supposed to have OH, but then when it forms an ester, it loses this hydrogen here, and everywhere else where I'm putting a dash, you fill that with hydrogens, right? And then the last part, propanoid, that is the acid. So propanoic acid was supposed to look like this, right? But what happens is that when it forms an ester, it loses this OH here, right? The alcohol loses an H, and then the acid loses an OH, and then the byproduct is then H2O, right? So let's put it in our structural formula. So here we're gonna have dash a carbon, an oxygen, carbon, and then there we go. So like I said, everywhere when there's a dash, we just put hydrogens, right? For the sake of time. Now let's do 2.3.2. 2.3.2 says the UPAC name of the organic acid used to prepare compound A. Yeah, we went through it, right? I say that the last part comes from the acid and the first part comes from the alcohol. It is saying prop, so we know that the acid that was used there should be propanoic acid, right? So 2.3.2, the answer is propanoic acid. And then if the question was saying let's name the alcohol, then it was going to be pentanol. 2.3.3 says let's name or give the formula of the catalyst that is used, right? In esterification, we always use H2SO4 or sulfuric acid. Question 2, organic chemistry. We have a table there. We have 6 organic compounds. And then 2.1.1 it says write down the letters that represents the following. 2.1.1 says a ketone. So A is an acid, B is an aldehyde, C is an alkane, D it's a haloalkane, and then E is an alcohol, and then F is the ketone. Why am I saying F is the ketone? I'm saying that because of the functional group. Let me do something real quick so that I can show you what I'm talking about. So here's the functional group here. This is the functional group for ketone. So as soon as I see that, I know that I have a ketone. So that is F. We have 2.1.2. 2.1.2 says 2 compounds that are functional isomers. Functional isomer. A ketone is a functional isomer of an aldehyde, and then a ester is a functional isomer of carboxylic acid, right? These are the only 2 functional isomers we have. So the only ketone we have is F. It has 1, 2, 3, 4, 5. It has 5. It has 5 carbons. Let's look and see if we have an aldehyde that has 5 carbons. E is not an aldehyde. D is not an aldehyde. C is not an aldehyde. B is an aldehyde, and it says pentanol. You know that it says meth, eth, prop, bute, pent, right? So it has 5 carbons. So the functional 2 compounds that are functional isomers is B and F. It's aldehyde and ketone. Let's move ahead. 2.1.3. 2.1.3 says write down the letter that represent a hydrocarbon. That's a alkane, an alkene, or an alkyne. For this question, the only hydrocarbon we have is number C, which is which has 10 carbons and 22 hydrogens. Let's move ahead. 2.2 says for compound D. Let's look at compound D. There it is there. I just put some brackets over it to highlight it. It says write down the homologous series to which it belongs. We know that it's a haloalkane, like we've already said. So we're just gonna go ahead and write that down. Why are we saying it's a haloalkane? It's a hydrocarbon that has a halogen, or in this case it has halogens because it has two bromine. There we go. That was 2.2.1. Let's move ahead to 2.2.2. 2.2.2 says write down the UPEG name of compound D. So we're going to calculate the carbons. So we have 1, 2, 3, 4, 5, 6, 7. We have these 2 here on the outside, and then 8, right? So as soon as we get 8, we know that that is going to be oct. So we have oct, and then it's a haloalkane, so it's just going to be octane. And then now we look for where the halogens are positioned. If we count from the right hand side, it's 1, 2, 3, and then if we count from the left hand side, is 1, 2, 3, 4. So the closest path to a halogen is from the right hand side. So we're going to have 3 comma, and then the other position for the other halogen. So that's 1, 2, 3, 4, 5. So it's 3 comma 5 dash dibromo octane, 3.5 dibromo octane. There we have it. Let's move ahead. 2.3. 2.3.1. 2.3.1 says consider compound F. Compound F is a ketone. It's a ketone. Then 2.3.1 says write down the UPEG name of its positional isomer. Okay, so positional isomer, same molecular formula, but different position of the functional group. So we have 1, 2, 3, 4, 5 carbons, and then the functional group is on this second carbon from the right. If we for an element to be a ketone, the oxygen double bond should be sandwiched by carbons, right? So we cannot put an oxygen here. It becomes an aldehyde. It's no longer a ketone. But then if we come and we put it on this carbon here, then it's going to be the same name, because we'll start naming from this side. So it will still remain what it is. So we are supposed to put it in the carbon in the middle. It will have a different position of the isomer. That's different UPEG name, but it's still a ketone that has the same molecular formula. So that's how we draw it. So we no longer have this. The oxygen double bond is there, and then you can fill out the rest of the carbons. So now the name becomes 1, 2, 3, 4, 5. That is pent, right? Pentan, and then 1, 2, 3. 1, 2, 3. If you count from any way, from the left or from the right, you get to the oxygen double bond after you've moved past 2 carbon. So that is pentan 3 on. And then that's it. That's how you name the positional isomer of compound F. 2.3.2 says a chain isomer of compound M, compound F. So still same molecular formula, but different structural formula. So again, let's go back to the basics. We have 1, 2, 3, 4, 5. And then we know that the oxygen double bond should be sandwiched between 2 carbons. So let's say it's still here. If you take this carbon here and then you put it here, that's virtually impossible because the carbon can only support 4 bonds. If you put it here, then you're gonna count from you're gonna start counting from this one because it's not, there won't be anything else here, so you'll start counting from 1, 2, 3, so it will remain the same ketone. But then if you don't do that and you take this carbon here and then you put it here, you're thus going to get a different chain, a different name, but still the same molecular formula. Yeah, maybe there's another way that I'm not seeing that you can use, but as long as you play around with it, it has a different name, it still has the same molecular formula, then you're good to go. So in this instance, if this is what we are going to have, it's going to be, let me see, it's going to be butane 2-one, right? So if this is 1 and we're saying this is 2, then this is 3. So we're going to have 3-methyl butane 2-one, and then that's a chain isomer for compound F. 2.4 2.4.1 says during the reaction of compound A with compound E, compound A is an acid, right? And then compound E is alcohol. There we go. And then you know that when you mix an acid and an alcohol in the presence of an acid catalyst, you're going to get esterification. So let's see. 2.4.1 says okay, they have reacted. It says write the UPEG name of the organic compound formed. So you know that if you have an alcohol and then acid, you add the acid and then you get the ester. At the naming, you start by the alcohol, right? The alcohol is in this instance 1, 2, 3, 4, 5, 6 is hexanol, right? So we have hexanol for the alcohol, and then for the acid we have methanoic acid. If you mix these two and you form an ester, this is how you write the name. You take the alcohol is hexanol, it will become hexyl when you start writing the name of the ester. And then this one says methanoic acid, it will become methanoid, methanoid. The spelling is just confusing me there for a second, but then okay, it's not really visible. Methanoid. Yeah, so that's it. That's the name of the ester. So if you add butanol, you're going to have butyl methanoid, and then for a different acid, you know what to do. So we done with 2.4.1. Okay, 2.4.2 says the structural formula of its functional group. That's the functional group of ester. So you have a double bond, and then you have an oxygen here, you have a carbon, and then it can be bonded to something there. This is the functional group. There's really no trick. There's no formula. It's just the functional group of an ester. Yeah. But if you pay attention to detail, you can see that this part will come from the alcohol, and then this part will come from the acid. But other than that, just straightforward. 2.5.1 compound C, 10 carbons, 12 hydrogens, reacts at high temperatures and pressure to form a 3-carbon alkene. 3-carbon alkene, so that's propyl. It has formed propyl, and then some alkene Q. And then the first question is write down the type of reaction that takes place. this is cracking. You can see that is this big compound, and then now it has cracked to P and Q. It's cracking, or you can even write elimination. This is also acceptable. Then 2.5.2 says molecular formula of compound Q. Okay, so we start with 10 carbons, and then we have 22 hydrogens, right? And then we have a 3 carbon alkene. So that's 3 carbons is an alkene. So this is supposed to be H of 2N, N is 3 in this instance, so that will give us 6. So what's left? 10 carbons, and then we subtract 3 carbons. We're left with 7 carbons, and then 22 hydrogens, and then we subtract 6 hydrogen. We're left with 16. So that is CnH2n plus 2. So this is so this is the question says we should write the molecular formula. So this is the molecular formula. This is the molecular formula we're looking for. And then 2.5.3 structural formula of compound P. We already know that compound P is propyl. So C. We can put the double bond here, or we can put it there. It doesn't matter. I will still have the same name. And then carbon, saturated, carbon, and then saturated. So yeah, there we have it.
Learners investigate factors that influence the boiling point of organic compounds. The boiling point of some organic compounds obtained as shown in the table below. And then 3.1 says define the term boiling point. So we know fully well that the boiling point is the temperature at which the vapor pressure is equals to the atmospheric pressure, right? So the temperature in which the vapor pressure is equals to the atmospheric pressure. But you have to write it in full. I'm just writing it like this for the sake of time. And then 3.2 says the boiling points of compounds A, B, and C are compared. And then 3.2.1 says, how do the boiling points vary from compound A to C? So we come in here from compound A going to C. So we have minus 42, minus 0.5, and 36. Clearly, the boiling points are increasing, right? So for 3.2.1, we're going to write increases. And then we have 3.2.2, which says, explain the answer to question 3.2.1. So why are these boiling points increases? When you're coming from A to C, you will realize that A has 3 carbons, and then B has 4 carbons, and C have 5 carbons. So we can see clearly that the chain length is increasing, right? So we can say that the chain length increases. And then it doesn't end there. What is the consequence of the chain length increasing? When the chain length increases, we'll have an increase in the strength of the induced dipole forces, right? So we're going to say that the strength of induced dipole forces goes up, and then in conclusion, more energy will be required to overcome the forces. So that's exactly what you're gonna write. More energy required to overcome the forces. I'm just gonna leave it like this for the sake of time, but you have to write it in full when you sit for your exam. And then 3.3 says the boiling points of compounds B, C, and D are compared. Is this a fair comparison? So let's go look at B. Here's B, which is butane, C, which is pentane, and D, which is methylbutane. And then, is this a fair comparison? If we look at the molar mass of B is 58, the molar mass of C is 72, and the molar mass of D is 72. So no, I don't think this is a fair comparison. And then obviously they're gonna ask us why, because compound B has a different molar mass, right? Has a different molar mass, because when we investigating, when we are doing these experiments in chemistry, we are only supposed to be changing the independent variable, right? We're not supposed to change the control, which we need the molecular mass to be. So if we were comparing only C and D, then that would be fine because they have the same molecular mass. Or if we were comparing A and F, but then as for B, it has a different molar mass, so it's not a fair comparison. So we have 3.4, which says the boiling points of compounds E and F are compared. So let's just erase this and look at E and F. So here's E, which is ethanol, and F, which is ethanol. And then 3.4.1 says state the independent variable for this comparison. So the dependent is what we're looking for, right? In this instance, it will be the boiling point. And now the control is what's kept the same, which is the molecular mass, right? We have 46 and 44. They're not really kept the same, but then they're pretty much close to each other. And then what we are changing here is the functional group, right? You can see that here we have ethanol, and here we have ethanol, alcohol, and then aldehyde. So the independent variable we can say is the functional group. You can even say is the homologous series, and it will still be fine. And then this is 3.4.1, my bad. And now we have 3.4.2, which says write down the name of the strongest van der Waals force present in compound F. So in compound F, the strongest is dipole forces. This question is more of content knowledge than solving any problem. And then 3.5 says which compound D or E has a higher vapor pressure. So the higher the VP, the lower the BP. BP being the boiling point, right? So compound D, which is methylbutane, has a boiling point of 28, and then compound E has a boiling point of 78. So the higher the VP, the lower the BP. Compound D has a lower boiling point compared to compound E. So we're gonna say D has the higher vapor pressure. As a consequence, they say give a reason. So the reason is what we just talked about. The higher the vapor pressure, the lower the boiling point. Clearly, methylbutane has a lower boiling point. As a result, it has a higher vapor pressure. If a compound has a higher vapor pressure, what does that say about the boiling point? What does that say about the melting point? Before we do that, let's do 3.1, which says let's define the term melting point. So melting point is the temperature at which the solid and liquid phase are at equilibrium, the temperature at which the solid and the liquid phase are at equilibrium. And then now 3.2 says, which one of C or D has the higher vapor pressure? Give a reason for your answer. So here we are given compounds and their melting point. So for you to be able to answer this question, you need to know the relationship between vapor pressure and melting point. So what is the relationship between the two? We know fully well that the higher the vapor pressure, the lower the boiling point. The same is true for melting point. The higher the vapor pressure, the lower the melting point. So between C or D, the one with the lower melting point has the higher pressure based on this relationship we're proposing. So which one between C or D has a lower melting point? It's clear to see that C has a lower melting point, right? At minus 16 degrees Celsius versus D, which has a melting point of 16.7. So our answer for 3.2, we would say C. And then why are we saying C? We are saying C because it has a lower melting point. We know fully well that the higher the vapor pressure, the lower the melting point. 3.3.1 says let's define the term structural isomer. So structural isomers are organic compounds that have the same molecular formula but different structural formula. The same molecular formula but different structural formula. Right? And then 3.3.2 says explain why B has a higher melting point than A. Refer to structure, intermolecular forces, and energy in your explanation. So A and B are structural isomers. They have the same molecular formula but different structural formula. So let's look at A. A is clearly branched, right? It says 2-methylhexane. So on the second carbon, we're supposed to have a branch. And then B just says heptane. So B is a straight alkane. That is the only difference between the two. And we're going to use that to explain our answer. So we are already told that B has a higher melting point. If B has a higher melting point, we will know consequently that it has a lower vapor pressure, right? Because the higher the vapor pressure, the lower the melting point. So here we have higher melting point, so we need lower vapor pressure. But why does it have lower vapor pressure but A doesn't have? So the difference between A and B is that B is less branched, right? As we are proposing, B is a straight alkane while A is a branched alkane. But then if it's less branched, then what will that mean? That will mean that we have stronger intermolecular forces. So we have strong IMF. Right? And then stronger intermolecular forces will mean that we need more energy to break bonds in compound B, right? So more energy are required to overcome IMF. Just to recap, we are comparing A and B. B has a higher melting point, so we know that it has lower vapor pressure. If it has lower vapor pressure, it has stronger IMF, and if it has stronger IMF, then it requires more energy to overcome the intermolecular forces, right? But then what's the difference between A and B? The only difference between A and B is that B is less branched. So this tells us that if you have two structural isomers, the one that is less branched will always have a higher melting point versus the one that is more branched. Now let's do 3.4. 3.4 says let's explain the difference in the boiling points of C and D, referring to the intermolecular forces and the energy in our explanations, right?
Let's go back to the basics real quick here. So we know that compound C, right, is an alcohol, and then compound D is an acid, right? So because compound C and compound D are with an alcohol and an acid, we know fully well that they both possess hydrogen bonding, right? We know that they both have hydrogen bonding, right? So we can say that they both have hydrogen bonding. But then if they both have hydrogen bonding, then why do they have different melting points and consequently different boiling points? That is because compound D, right, which is our acid, has two sides of hydrogen bonding versus compound C that has only one side of hydrogen bonding. Now the question you're asking yourself might be, wait a minute, what are we talking about? Why are you saying compound D has two sides of hydrogen bonding? That is because acids can go under a process called dimerization, right? And then alcohols cannot. So we say that compound D has two sides of hydrogen bonding, right? If it has two sides of hydrogen bonding, then what does it mean? It means our compound D has stronger intermolecular forces, right? And then what do we know about compounds that have stronger intermolecular forces? They require more energy. They require more energy to overcome the intermolecular forces. And if it requires more energy to overcome the intermolecular forces, then the boiling point of compound D, right, will be greater than that of compound C. But1 an unsaturated hydrocarbon, and compound X, a saturated hydrocarbon, reacts with bromine as represented by the incomplete equations below. 4.1.1 give a reason why but1 is classified unsaturated. It is classified unsaturated because it has double bonds, right? If an organic compound has double bonds or triple bonds, then it is unsaturated, right? It can still go under addition reaction. So 4.1.1, it contains a double bond. So it contains a double bond. Now let's move to 4.1.2, which says that what type of reaction, addition or substitution, takes place in the following. Reaction 1. Reaction 1, we have but1 plus bromine, right? Because this organic compound here is unsaturated, it can only go under addition reaction, right? And then now we can move to reaction number 2. Reaction number 2, we have X, which is said to be a saturated hydrocarbon, right? So it's an alkane, and then we are adding bromine. So an alkane can only go elimination or substitution, right? But then we are already told here that we have to choose between addition or substitution, right? So clearly our answer here will be substitution. So for B, we have substitution. 4.1.3, write down the reaction condition necessary for reaction 2 to take place. For reaction 2 to take place, we need heat, or we need sunlight. But from sunlight, we're still looking for heat from the sunlight, right? Or we need UV light. And then 4.1.4 says, write down the UPEC name of reactant X, right? Reactant X is a hydrocarbon, and when we substitute bromine, we get 2-bromobutane, right? It should be quite clear that the UPEC name of reactant X will be butane, right? A hydrocarbon. And then 4.1.5, write down the name or formula of product Y. Okay, so again, when we have a chemical equation, whatever that is on the left must be present in the right? It needs to be balanced. So we have butane, right? And then we add in bromine, and then we get 2-bromobutane. So in place of a hydrogen in butane, right, a hydrogen is replaced with bromine, right? And in place of bromine here, we're replacing it with the hydrogen. So Y will be hydrogen and bromine, right? So what is the it is the name of the formula of product Y. So let's not complicate our lives and try coming up with the name. Let's just say HBr, hydrogen bromide. 4.2 says 2-chlorobutane can either undergo elimination or substitution in the presence of a strong base such as sodium hydroxide. 4.2.1, which reaction will preferably take place when 2-chlorobutane is heated in the presence of concentrated sodium hydroxide in ethanol? Write down only substitution or elimination. So if you pay attention, you will realize that concentrated is in bold, right? So that will give us an idea of the knowledge we're supposed to apply. So what is the knowledge that we're supposed to apply? If the base is dilute, we go under substitution. If the base is concentrated, we go under elimination. So since here we are told that the base is concentrated, we are going to go under elimination. If it was dilute, we're going to go under substitution. And then 4.2.2 says write down the UPEC name of the major compound formed in 4.2.1. So we had 2-chlorobutane, right? And it is going under elimination. So when it goes under elimination, we are going to lose the chloro, right? And we're going to be left with but2-ene. So 4.2.2, we have but2-ene. And then 4.2.3 says use the structural formulae to write down a balanced equation for the reaction that takes place when 2-chlorobutane reacts with a dilute sodium hydroxide solution. Now we're using a dilute base, right? And I've said that if we use a dilute base, we go under substitution, and if you use a concentrated base, we go under elimination. So let's write a structural formula for the substitution reaction that would take place. I will start by writing the structural formula of 2-chlorobutane, right? So we have 4 carbons, 1, 2, 3, and 4. And then on the second carbon, we have chloro. So let's have our Cl there. And everywhere else, we just have hydrogens, right? So let me just fill them in real quick, and then we move to the next step. So we're saying that we're using dilute sodium hydroxide solution, right? So let's have plus NaOH, right? And this is going to give us, now the substitution happens, right? How does it happen? This OH here is going to replace the halogen Cl, right? So if that happens, we're going to get 4 carbons again, and then in place of the Cl, we have OH, right? Instead of a haloalkane, we now have an alcohol, right? And then we have a hydrogen, and then there goes another hydrogen. And then plus, we know that in a chemical reaction, whatever you have on the left, you should have on the right, right? So we're going to have NaCl